This is a video for COM 442 and 6421 compiler design. In this video, I'm going to describe what needs to be done to achieve assignment number 3, which the topic is the generation of an abstract syntax tree for the program that you are currently parsing and compiling. So as you know, in assignment number 2, what you had to do is to build a parser. So now what you have to do for the following phases is to be able to have an intermediate representation of your program that you will essentially traverse in order to do the semantic checking and the semantic translation or code generation. So now what you are to do in assignment number 3 is from the parse using syntax directed translation, you will actually build this abstract syntax tree that will be this intermediate representation that assignment 4 and assignment 5 will essentially traverse this abstract syntax tree data structure that you will create now in order to do the phases of the back end of the compiler. So essentially, assignment number 3 is the end of the creation of the front end of the compiler that is going to generate an intermediate representation of the program that is being compiled. So let's first go to the assignment handout itself. So you'll find it here under week 7 handout here. There's a zip file. If you open the zip file, it's going to lead you to this folder here. So there's plenty of things in there. First of all, let's go to the README file. So the README file is as such. So of course, the PDF is the handout, which I'm going to quickly present after that. Then, well, as you saw in assignment number 2, one of the first step of assignment number 2 was actually to create or to transform the initial grammar that I gave you into an LL1 grammar. As you have seen, this is not an easy affair, and it's likely that some of you did not succeed in having a correct grammar, let's put it this way, to implement for your parser. If that's your case, if your grammar was proven to be wrong, then you can actually, I'm providing you with one grammar, the one that is presented here in the handout. So I'm giving you an LL1 grammar that corresponds to our initial grammar. Now I have tested it using the A2CC tool or the FLASI tool that you can find online, so that you can take this grammar, transform it into A2CC format using the grammar tool that I gave you in assignment number 2, and then import this grammar into A2CC, and then you can actually use these cases here, which are essentially a token stream that the A2CC or FLASI tool can read, and then check if you can derive this stream of tokens from this grammar. So this is how I tested this grammar to check that it's actually correct. So you don't have to use this grammar. You can, if you are satisfied with your own parser as it is now, then please go ahead and you don't have to use this grammar. So if you had trouble with your grammar and your parser in assignment number 2, you may somehow reset and actually start afresh with this particular grammar here. Just to make sure that people don't get stuck assignment number 2 if their parser is mangled, right? Okay, other things, as I will explain later, I'll come back to that later. There is one of the requirements that I'm asking you for assignment number 3 is that you should output to a text file a representation of the AST, okay, so that the marker or yourself can actually see or be able to inspect whether or not the AST is correct. You will have to create a data structure, which is a tree, And it's not necessarily easy to inspect the result of your parser if it's generating such a thing as a tree. Right? How can you visualize somehow or traverse the tree to check that it's entirely correct? So that's why I'm asking you to produce essentially a function that's going to traverse your tree and then generate into a file a representation of this tree in text. Okay. Now, what I'm proposing here is two different approaches. Well, the main requirement is that you be able to output to a file a representation of your tree so that the marker or yourself can actually inspect if the AST that you generated is correct according to the source file. So as you will see, if you open this file here, it actually represents a textual representation of the tree. So here, examples. So if you open this one here, the AST, just a minute. Okay, that's better. So this is, for example, a text representation of an AST that I have generated for an example program. Note that the example programs that I'm giving you there, they're not following the grammar that we have now. It's just an example of a certain program and then its corresponding AST text representation. Okay, so clearly here you see that this is the prog node, which is at the top, and then here you have the class list. Then in the class list, you have a class, and then in this class, for example, you have the name of the class, and then the list of data members that are in this class, okay? And so on and so forth. So you see that it's kind of easy to actually visualize the tree. Okay, so how would you generate that? Essentially, after you have the data structure, which is your AST, then you create a function that actually traverses the tree in depth first search, and then for every node that it comes into, will output a line of text here. So as you do depth first search and output for every node that you traverse a line of code there, then that enables you to essentially output the AST in this file here. Another alternative, if some of you may know the dot language, and for example, a viewer named Dotty, which I have installed on my computer, which is outputting something like this, which of course is much nicer to see, but it assumes that you know the dot language, and that let's open the file here. So you see this is the code, essentially the dot code that corresponds to this graph. So the idea is still the same. So you do a depth first search of your AST, and every step of the way when you encounter a certain node, then you generate a piece of code here. Okay. You don't have to do it this way, but of course it's much better to visualize. I know that a lot of people know about this tool. So if you already know, that might be natural to you. If you don't, that actually is a very good tool to learn how to use. Right? Okay, so and I'm asking you to have this visualization. I remind you, it's not only for the marker, it's also for you. Because as you will do this AST generator, then every step of the way you want to see the tree that you are generating. Okay, you have to be able to inspect this tree to see if it's correct. If you don't have such a visualizer, it's going to be hard to figure out if it's correct or not. Okay, so it's important that you don't take this as an afterthought, but you see this as a tool that you will use in the process of designing the AST generation. And then there's some source files that I'm providing you, which are exactly the same source files as I gave you since the beginning. Okay. Now let's go to the PDF itself. Okay, so the deadline for it is March 5th. So that's essentially the last day of the spring break. So you haven't from now, the week before the spring break and the spring break to actually do this, this assignment. In terms of amount of work, you should not underestimate the first steps, because I will explain what are the steps involved in this later after I briefly explain what is required from as explained in for the assignment, as explained in the PDF, and then I'm going to explain more as to what is the process of doing that. So you should don't think that this is a programming assignment, right? You may think so, but it's more the preparation for the programming that is important. Just like for the assignment number 2, in fact, preparation for the assignment was transforming the grammar into LL1. That was the actual real problem. Okay. So it's a bit similar here. The preparation for the implementation is what is the real problem. If you try to find your way through this problem as you are programming, you will have a lot of difficulty. So that's one of those problems where you have to think before you actually start programming. If you don't think before and you think you're going to be able to think as you're programming, inevitably you're going to make some mistakes, and then it's going to be very difficult. Okay, so first of all, there is a simple document that I'm asking you to provide, which are somehow forcing you to across the steps that I'm telling you that are required to solve this problem. First of all, you need to provide what is called an attribute grammar. What do I mean by that? If you look in slide set number 7, or let's go to 8.5. So that's one of the slides that I gave here, or the explanations I gave as to how to do that. So this, what I have here, is an attribute grammar. So it is your LL1 grammar into which you have inserted some semantic actions. So that's what is an attribute grammar. So the first thing I want you to achieve is to write down the attribute grammar that corresponds to the implementation of your parser that will eventually do the generation of the AST through syntax-directed translation. Okay. So what is the attribute grammar? It's simply your LL1 grammar where you have inserted the semantic actions into the right-hand sides. That's what is the attribute grammar. So I invite you, if you were not in class, it's very important that you look at the slides, slide set 8 and 8.5. That will describe to you the process of generating or creating the attribute grammar. And also, you must provide me with a description of the design of your AST generator, what tools that you have used in the process, and so on and so forth. The main thing, of course, to implement is the parser augmented with some syntax-directed translation. So depending on if you're using a recursive descent predictive parser or table-driven predictive parser, the procedure, of course, is different, but both amounts to say that you're implementing a attribute grammar. That basically you insert some semantic actions or function calls inside of your right-hand sides so that you use a semantic stack to actually push the AST nodes and pop the AST nodes, as I have explained in class. So in terms of programming, that's the main thing that you have to do. Take your existing parser. You don't have to change it. You just add semantic actions that are being called at the right places. And you have to add, of course, the corresponding semantic stack that is holding the nodes. Okay. Of course, and also that means that you need to create a data structure for your abstract syntax tree nodes, as I also explained in class. Second thing that you need to implement is the output, the AST output in a text file, as I've just explained. So either you have a plain text file that is presenting some kind of tree using text, or I propose that you use the dot language to represent your AST so that you can use dotty, or there's also viewers online that you can give your dot code and then it shows you online a graph representation of this dot file. And then I repeat, very important, don't take this step here of AST output generation as an afterthought. It is going to be a tool that's going to be very, I might say, even necessary for you to actually verify every step of the way that you're generating the right AST. Another thing that I said repeatedly in class also is that you should not try to do this in a whole, the generation of the implementation of the syntax-directed translation. I highly suggest that you start with a subset of the grammar, then inject the semantic rules in a subset of the grammar. For example, you may start as in slide set number 8.5. I give the example as to how to do it for a variable declaration. So for example, you could start with that, and then you look in your grammar, what are the rules that are involved in parsing a variable declaration? And then you insert the rules in your right-hand side only for that. And then you actually start your parser, and then you check if it generates the right tree for every variable declaration that you have in your program. Okay. Then once you know this works, then you can do for something other, like for example, a function header or a class declaration. So you proceed incrementally like this so that you can verify every step of the way if it is actually working. Why is that so? Because if you do a big bang, integration of all your complete attribute grammar in the parser, if there's one thing that doesn't work, maybe you're going to be able to find your way out of the problem, but it's much more likely that there's going to be at the same time many things that don't work at the same time, which is going to be very hard to figure out where things are going wrong. Okay, so very good advice is to proceed incrementally. You start with something small, you check if it works. You add something small, check if it works. And then you're going to proceed incrementally like this, and eventually you're going to be able to generate the AST for everything. Okay, so proceed incrementally. And then once you proceed incrementally like this, if you have your AST output, then you can verify easily if what's on the ASTs that are on your stack are actually correct trees according to what you intend to do. Then, of course, you must provide test cases that cover a broad range of different situations, and you somehow show that they generate the right ASTs. And then finally, you must provide a driver that enables the marker to actually run all the test cases and eventually check that everything is working correctly. Okay, so this is what you have to do. So what about how to do it? So let me go back to the Blackboard. So this is a procedure that I'm not only proposing, that I'm telling you this is the order of things that you need to achieve. So first of all, you need to determine the list of semantic concepts that are in your language. And then what you need to do, the second step, is to determine what is the structure of all AST subtrees that correspond to each of the concepts that you have identified in your language. So that has been explained in slide set number 8, if you recall. So let's go back to this. Of course, here I'm not going to re-explain everything again, just pointing to you where to go if you want to know how to do what I'm referring to here. So this is slide set 8. In slide number 33 here, you have the language that we are analyzing in the slide set. It's not the same language as you have in the assignment. It looks very much like the same, but there are some differences. Okay, so important to understand that the concept that I'm identifying on the slides, they're the concepts in this language. For yours, it would be slightly different. There's a lot of intersections, but not exactly the same. So you can't take what's on the slide and apply it directly to your project. Okay, so this is the grammar here, important. This is the original grammar. This is not the LL1 grammar. So what you're analyzing at this point is the LL1 grammar to identify what are the concepts in the language. So what are the concepts in this language? For example, there's the top concept, which is a program. So in this language, what a program is a list of class declarations, followed by a list of function definitions, followed by essentially the main function. Okay. So, and you try to imagine what would be the tree or the subtree that will be represented by, or representing this highest level concept. So here, for example, it's prog, where you have a subtree for class list, subtree for function definition list, and a subtree for the main function. Okay. So for every concept that you identify in the language, then you define a subtree for the AST that will be generated to represent this concept. So it's very important that you define this before, because the whole idea is to generate this tree. If you're trying to design your parser and you have no idea what this tree will be, it's almost impossible to find your way through. Okay, so the best thing to do is to first identify what are all the different semantic concepts in this language, and then to define by what AST subtree they will be represented. What's the shape of the tree that will be representing this concept? For example, here, the shape of a program, AST, is there's a parent node on top named the prog node, and then there's a subtree for a class list, a subtree for the function definition list, and a subtree for the main function. So it's an AST node of type prog that has 3 children of each of these different types. Very important, as I mentioned in class repeatedly, that or sometimes, that your nodes, your AST nodes, they must be of different types. Okay. So you might think of designing the AST data structure and that there would be only one type of node across the tree. We will later use the visitor pattern to traverse the tree. So, and this requires that each of your nodes have a different type, depending on what concept they represent. Okay. So you must have, for example, here, an AST node of type prog, and so on and so forth. So each of your different nodes will be each of different types, of depending on what concept they represent. That's to enable the use of the visitor pattern in the backend. Then, for example, and then you break down. So that's the topmost concept, right? So here I have identified another sub-concept of the language, which is the class list. So what is the subtree? Because the triangle here, what it represents, essentially, it's an abstract representation to say that there is a subtree. So what is the shape, for example, of the class list subtree? The class list subtree is of this shape here, where on top of the tree, there is a node of type class list. And then it has n number of children. That's what the dot dot here represent. That's n number of children. Each of the children are of type class declaration. So then if you look at the next slide, then you have the definition of what is a node or a subtree a subtree of type class declaration. So a tree of type class declaration has 3 children: the name of the class, the inheritance list of this class, and then the list of members of this class. So you see that the shape of this tree is that parent is of type class declaration, and it has exactly always 3 children, which is an ID, which represents the name, and a tree, a subtree for the inheritance list, which is a list of ID that represents the list of classes that are inherited by this class. And then so on and so forth. So again, I have explained that in the lecture. You can listen to the video if you want to hear it again, or if you didn't come to class. So the job here is essentially to identify first what is the list of all the different semantic concepts that are in this language by looking at the original grammar. Then for each of these semantic concepts, you try to imagine what kind of shape of an AST each of these concepts will be represented within the AST that represents a particular program that uses this concept. So, okay. So that's how you actually achieve step 1 and 2. First, determine the list of semantic concepts from the original grammar, and then determine what is the structure for each of these concepts you have identified here. What is the structure of the AST subtree that will eventually represent each of these concepts? So you'll find the explanation for this in slide set number 8. Then the next step. So after this step here, you will have a very good idea, a very precise idea of what will be the shape of this tree that I'm generating, that you are generating. So that's the objective of these 2 first steps here, that in your mind you have very good conceptual representation of what will be the shape of this tree that you're generating. And depending on what concept you are parsing, what kind of tree you are now generating, right? Then what you need to do is to construct the attribute grammar that implements the AST construction process. So that I explained in slide set 8.5. So let's go back to that. 8.5, okay. Well, as I hinted at before, what's happening here is bigger, it's not. So essentially what you want to do here, again, I'm not gonna re-explain everything, but what you want to do here is to create an attribute grammar, as I hinted at before. What an attribute grammar is your, in this case, it's your LL1 grammar that is represented in your parser. Okay. So for this step, you're looking at your LL1 grammar. The first 2 steps were determined by using the original grammar. Now, what you have to do is to take your LL1 grammar and then inject some semantic actions that are creating nodes or subtrees, and then inject them at the right places in the parsing process. Okay. Not going to repeat everything here, but I'm just going to give you some hints about what that means. So for example, when you are parsing a variable declaration, again here, this is not exactly the same syntax that you have in your language, but it's very similar. Here, this example is showing how to do that for a variable declaration. This is here a variable declaration. So when you parse a variable declaration, eventually you're going to go let, you're going to match let, match ID. And then the thing is that when you match ID, then you know that you have encountered and successfully parsed a semantically meaningful token. So here, ID here refers to a variable that's going to be involved in this case. It's going to eventually be a variable declaration. So this ID here is in fact the name of the variable that you are declaring. So it's a semantically important concept. It's actually an atomic semantic concept that you've just identified. So now you will fire, or you will create this semantic action that is actually creating a leaf node for an ID, and then we'll push it onto the semantic stack. Okay. So every step of the way, when you find a completed semantic concept, right after the completion of this semantic concept, you will insert a new rule that is going to create either a node or a subtree for this completed semantic concept. Okay. For example, as you are continuing, let ID, then you push the ID here, the AST node for ID here. And then you go colon, and then you go type. And here you go into another right-hand side. And then be it a, if you're using a recursive descent predictive parser, that means you're going into another function. And then after you, for example, after here you parse, for example, integer, then this is another semantically meaningful token that you have just identified. So after you identify integer, which in this case is the type of the variable that's being declared. So then you create another rule that will actually create a leaf of type, and then create this AST node and then push it on top of the stack. Okay. So now what you have on the stack is the name of the variable and the type of the variable. So then after you return from this type definition here or rule, and you go to array size. And then when you go to array size, well, okay, so here essentially when you have a list of indeterminate number of elements, then eventually you're going to need to pop nodes from the stack in order to create composite concepts. So if this composite concept involves n number of sub-concepts, then you're going to have to pop n number of things, and you don't know how many of these things you should pop depending on the situation. So a trick here is to essentially push a marker node onto the stack. So this epsilon node here essentially denotates the end of the list of dimensions of a variable. Okay. So this marker here, or this semantic rule that I fire here, is pushing a node here that represents the end of the list. That's going to make me stop popping nodes when I'm going to create the sub tree for the array size. Then I process, so I essentially inserted my epsilon node when I was here, right? And then I process the array size repetition. And then every step of the way, when I see an int lit, which is, for example, the 2 here first, then 2 is again a semantically meaningful token that I have identified, which is the size of the first dimension of this array. So then I create another semantic rule A2 that is creating a leaf of type int lit and then pushing it onto the stack. And then I go close square bracket, and then I go again array size repetition. So I go back here again, open square bracket, and then another int lit. This time this one here, which is 3. So then I create a node by firing this rule. I create a node int lit 3 and then push it onto the stack. And then I do again array size repetition, but then eventually I find this is epsilon case, in which case I actually go back here. I go back here and then actually fire this rule A3 here, which what it does is to create a subtree for the composite semantic concept array size, which is actually a AST node that has n number of children, n being the number of dimensions of this array. So I pop, so that's what this does here. When I call this A3 here, it creates a subtree of type array size, as I'm creating here. And then I pop until epsilon. So I pop 3 to epsilon, and then I make all the nodes that I popped, excluding epsilon, and I make them children of this node here. And then I push this onto the stack. So at this point in time, what I have is, in fact, I have 1, 2, and then 6, which is the array size onto the stack. So you see here that I have now on top of the stack my 3 sub-semantic concepts of the composite concept variable declaration. So the only thing I need to do then is when I come back here, call v2, which will pop these 3 nodes from the stack, create a node of type variable declaration, make each of these nodes a child of this new node, and then push this node onto the stack. So thus, I have successfully generated an AST, a correct AST for this variable declaration. Okay, and this AST is this one here. Okay. Now, as I explained in class, one of the things I find is useful is to actually draw on a piece of paper an example of, for example, one here variable declaration, and then you can visualize what parsing tree is being traversed by your parser as this is happening. And then that helps you to figure out where to inject the different semantic rules. So at every step of the way, when you encounter a semantically meaningful concept, such as, for example, ID, integer, intlit, and so on, then you see that here you need to create a node for ID, create a node for integer, create a node for intlit, and so on and so forth. So by having the tree visualized on a piece of paper, I believe it makes it easier to actually figure out the procedure that you need to implement, or how to create your attribute grammar. Okay. So that's basically what is the process of creating the here. My step number 3 was construct an attribute grammar that implements the AST construction process. So you see here that I've shown you how to do this for a variable declaration. That's what I suggest that you do, that you start with something simple, that you have a better understanding of how it should be done, and then you make it work for this simple thing. Then you select another simple thing that you think is similarly simple, and then you do it for this other thing. And then every step of the way, when you do a new one, then you put this in your parser, you put this, the representation of this, attribute grammar, you code it into your parser. So that your parser, for example, in the first step, it will do only the generation of the AST for any variable declaration that it encounters. And then you can fire your parser after you injected the code for generating the trees for variable declarations. Then you fire with your parser that parses a program that has variable declarations or one variable declaration. And then you check if it actually generates the correct tree. And that's where your AST output into a file comes in handy to actually check easily that the ASTs that are on your stack are the correct ASTs. Okay? And then you proceed incrementally, and then you do each of the different subtrees that you have identified here, corresponding to each of the different concepts. Then you do them one by one, of course, incrementally using one another. For example, and the variable declarations are, for example, they can be either local variables in a function, or a similar concept is the data member of a class. Okay. And then you proceed incrementally and up in the tree by aggregating each of the semantic concepts that are subordinate concepts to a higher level concept. So you start from the subtrees, and then you aggregate to higher level supertrees that are representing higher level semantic concepts. So very important that you don't try to do everything at once, as I explained before. If you do everything at once, very likely that you're going to have made more than one mistake, that it's going to make it very hard for you to figure out where it's actually going wrong. Okay. So you proceed incrementally in small steps and then verify if it's okay. Do another step, verify if it's okay, and so on and so forth. If you try to do everything at once and it doesn't work, which is very likely, then it's going to be very difficult. Okay, and then in conjunction with this here, as I just explained, after you determine the attribute grammar for a portion of your grammar, then you inject or translate this attribute grammar into an implementation. Now, where is the representation of how you implement an attribute grammar? Well, depending on if you have if you implemented your parser using a recursive descent predictive parser or a table-driven predictive parser, you might want to go to either slide 7 or 8. So let's go to 7. Okay, let's go to 7. Sorry, need to share. Let's go to slide 7. So if you have a table-driven predictive parser, then, as I explained earlier, what you need to do is literally you take your attribute grammar and then which will have inserted the semantic rules inside of the right-hand sides. So essentially, you take these these new right-hand sides in which now there are symbols that represents the semantic actions, and you change your right-hand sides with the new right-hand sides in which the semantic action symbols have been inserted. So that when your parser actually retrieves, when your parser fetches something in the table or looks up in the table, and eventually, for example, this basically says if you have E on top of the stack and you're parsing an ID as the next token, then you should apply rule number 1. So essentially what that means is that you will take this and you'll actually push this right-hand side in reverse order on top of the stack. So you see here that previously you would actually have put E prime T on top of the stack. Now what you will put on top of the stack is B E prime A T, where A and B are new kinds of symbols that you have now created that represent a certain semantic action. Okay. And then you need to augment your parser algorithm with only another case here, because here there was in your while loop, there were 2 cases. If the top of the stack is a terminal, you do this. If the top of the stack is a non-terminal, you do this. Then you have a new case. If the top of the stack is a semantic action, then what you do is simply call a function that corresponds to the implementation of this semantic action. That is, for example, either creating a node, leaf node, and pushing it on the stack, or popping some nodes, some children nodes from the stack, creating a new concept node, and then making these nodes that you just pop from the stack and making them children of this new concept. And then you take this node of the new concept and you push it onto the stack. So you see that it's quite simple for the table-driven parser. Not to say that it's much more complex in the recursive descent. Again, it's in fact exactly the same concept. So let's, which is explained in slide set number 8. Okay, so let me just use this one here, because as I explained earlier, if you want to do syntax-directed translation using recursive descent predictive parser, you have 2 options. The traditional option is to do the attribute migration by passing parameters across your functions, right? But I also explained how you can actually use a semantic stack to achieve the same. Okay. Remember that if you are when you are passing the parameters to your functions to do the attribute migration, you are effectively using the function called stack of the execution of your parsing functions as your semantic stack to do the attribute migration to achieve, in our case, the generation of the AST. In this case here, you're essentially defining your own semantic stack, and you let each of the functions to actually create nodes and push them on the stack, exactly as I just described before that the process is doing, right? So you have a choice here. Either you do the attribute migration using parameters to your functions, or you create your own separate stack that you push and pop the nodes from, the AST nodes from, and to. So then what you need to do is to somehow inject some code in your functions that is, in fact, implementing the semantic actions. So, for example, if you have, let me go here. Okay. Let's say you would implement the variable declaration function for a recursive descent predictive parser. So eventually, when you execute the function that implements this rule here, it will eventually match let, match ID, and then match semicolon, and then call the function type, and then call the function's array size, and then match semicolon, right? So that's what it would do. Now, after you have your attribute grammar, then what it would do is match let, match ID, and then implement some code that does this semantic action here, which is still to create a leaf node for the ID that you've just parsed, and then push this node onto the stack. Then match colon, then call type. Then when you call type, and you, for example, branch here, when you match integer, then you would put some code that implements the rule, semantic rule for T, which is to create a leaf of the type integer and push it onto the stack. Okay? So it's exactly the same procedure, except that what you inject in your code is not the actual symbols in the right-hand side. It's actually code that you put inside of your parsing functions. Okay, so you should see it as there should not be any difference in the procedure that I described here until you actually come to put your code in your parsing functions if you have a recursive descent predictive parser. So you still would have to create your attribute grammar, but then once you have the attribute grammar figured out, then the procedure to put that into action in your parser is to essentially follow this attribute grammar here, and then here you would actually insert some code inside of your parsing function that does these actions here that these semantic actions are representing. So that's what is represented here as the red code. Okay. So you see that here. Well, let's say, for example, let's go to f. So if in the function f, if you are parsing, if the factor that you are parsing is an ID, then you create a node of type ID and you push it onto the stack. Okay. And the same concept is for everything else. So you look at your attribute grammar that you have designed before, and you see where these actions should be inserted inside of your procedures, right? So this is how you achieve this entire assignment. So again, you should not see it as very different if you have a table-driven or recursive descent predictive parser. It's only the final implementation step that is different. All the preceding steps should all be the same. Okay. Is there anything else? This I already said. Just checking my list here of things. No, that's about it. So, okay, so very important that you, as I will reiterate that, that you don't think of this assignment as being a programming assignment. It's not about, I'm going to write this assignment, I'm going to sit in front of my computer and start coding. If that's how you proceed, it's going to be very long, very frustrating, and very confusing. The procedure is as I've described here. You should start by looking at the initial grammar I gave you, try to determine the list of semantic concepts in this language. Then, for each of these semantic concepts, try to imagine what will be the AST, shape of AST that will be representing each of these concepts. And once you have that, then you go to your LL1 grammar, and then you try to construct an attribute grammar that represents a procedure of creating an AST for the concepts that are being parsed by your right-hand sides, okay, as I explained before. Then once you have figured out for a sub-concept, then I strongly suggest that once you have it for a concept, a little part of your grammar, you construct the attribute grammar, for example, for a variable declaration. Then you put this into your parser, and then you execute your parser and you see if it's constructing the right tree. Of course, you should try it for different cases to make sure that it works not only for one case. So that's why it's important to have a variation of test cases, right? So that's about it for this description of the assignment number 3. Thank you.